Welcome to my presentation based on the topic Updating Service-Based Software Systems in Air-gapped Environments. Without further ado, I'm going to present you the motivation behind the topic, what is the problem and why it is interesting. Contemporary software architectures have shown the trend towards breaking down software into increasingly smaller pieces over the last couple of decades. Combined with nowadays popular agile methodologies, it results in releasing frequent updates to a fleet of products. With the rise of cloud and edge computing, we've gotten very much comfortable with the fact that software products are usually reachable via internet and updates can easily be distributed. However, this quickly becomes a problem when an air gap is incorporated, a prevalent choice in different sectors, including both private and public organizations, where data security is a fundamental requirement. CTPTO faces the introduced problem. We've adopted multiple custom software service-based applications which exchange data through an air gap, making the applications dependent on each other. As far as the scientific community is concerned, it is a novel and unique problem which is in addition backed up by real-world setting. To understand the setting better, let me introduce you this airborne photograph taken from a helicopter during the Integrated Field Exercise 2014 in Jordan. You can see the location of the software systems which are clearly scattered across the base of the operations. This is a detailed view of the software system from the previous slide. Most of the application services are containerized. Here you can see that the applications exchange data, the arrow shows it, and the dotted line indicates an air gap. So in most of the cases, they exchange data through air gap. My intention of showing you this diagram is not to go into the details, but to demonstrate the high complexity we face. Let us summarize the problem in just one sentence. How to update air-gapped service-based systems yielding verifiably correct combination of services with an emphasis on containerization technology. Further, I would like to present you the key idea of how to solve the introduced problem. The figure illustrates a bird's-eye view of the problem and solution domains. Let's walk through the diagram from the left to the right. On the problem domain, a series of air-gapped systems host software services, each having some versions. Those comprise the service version combination state, which is assumed to be known. Some services depend on other services based on the versions. Again, there can be an air gap in between. Now let's talk about the solution domain. To perform an update on an air-gapped system, the process entails first resolving of service dependencies, which means essentially getting a valid service combination, then copying corresponding artifacts, for example container images, from repositories to make them offline accessible. Afterwards, the air-gapped system is visited, the service combination is again verified against the local state, and if nothing prevents it, the update is performed. Further, I present the architecture of the software solution together with the update workflow. I illustrate the process by showing the responsible architectural parts and the corresponding user interface. The diagram illustrates functional architectural components of the proposed solution. As you can probably immediately tell, the architecture itself is service-based. So let's walk through the major components. The user responsible for the preparation of an update selects an available system and defines which of its services are subject for an update. For example, here the user selects the Geospatial Information Management System. Then he or she wishes to update simply all services, namely frontend, GeoServer, database, etc. Step 2. The dependency resolver delivers a satisfiable combination of service versions. Here, a procedure is applied to get all correct combinations, so the user may pick a version from available ones. Later, I will explain what dependency resolution procedure do we employ. Step 3. The core service prepares the corresponding artifacts by copying them from external repositories and creates a deployment plan. Here you can see again the corresponding user interface. The downloading part has not been visualized. Last but not least, given the deployment plan produced, the target air-gapped systems are physically visited, the update combination is verified again against the local service combination, and if possible, the update is applied. You may have noticed already that dependency resolution lies at the heart of the update workflow. Therefore, I want to describe it more. First of all, for the dependency resolution, we leverage satisfiability modular theories, where solving consists of deciding the satisfiability of a formula in first-order logic. The implementation was done using PySMT library, which conveniently provides a layer of abstraction, decoupling the SMT procedures from the underlying solvers. In our case, we use MathSat solver. Secondly, it adopts the so-called semantic versioning, where three numbers separated by a dot are used, for example, 2.4.1. We employ two strategies, AllVer and MaxVer, to calculate a right combination of service versions. MaxVer derives only the most recent service versions, whereas AllVer finds all suitable version combinations. MaxVer is intuitively less computationally expensive and is the preferred strategy to use. However, with AllVer, the user has more flexibility and the performance is acceptable for small input sizes. Last but not least, I would like to present the evaluation. Our evaluation goals are twofold, as we seek to investigate the performance in realistic setting, assessing dependency resolution over typical problem sizes, and the applicability of the proposed solution in practice, considering a realistic scenario and a mission-critical setting elicited from CDBTO. On the graph to the left, you can see the time it takes for the algorithm to resolve dependencies, y-axis, and how it grows when the number of services increases on the x-axis. You can see the differences between 50 and 125 versions per service. Considering only the realistic problem sizes, this would be up to 15 services and 50 versions each. The performance of the algorithm shows good results. To the right, you can see the memory consumption, which lies within 10 megabytes and can be arguably neglected. Next, we consider an evasion scenario, which was elicited via interviews from the key stakeholders and built up a characteristic scenario, a characteristic case where an air gap update is required. Imagine an unsatisfaction is dispatched to a remote location. Also, software systems are carefully prepared and shipped fully provisioned during the launch phase. The inspected state party, the nation or state in which inspection is performed, provides its own piece of equipment to conduct radionuclide measurements in a mobile laboratory. This results in developing an update to a system called laboratory application, which introduces a breaking change to 4 other air-gapped services. They must be updated too. On the diagram, the service in red is the one that initially must be updated. As said previously, updating it introduces a breaking change, so other services highlighted in orange must be updated as well. Thereafter, the solution is applied to the scenario. Then the stakeholders are interviewed for feedback and their opinion. Finally, the whole process is analyzed and pros and cons are identified. Last but not least, I would like to present the evaluation. Applying the proposed solution to the described scenario showed the following advantages. The solution provides a valuable overview of what is installed where and of what versions. The user gets an easy-to-follow plan. Admitting the right combination of service versions is backed by satisfiability. The executable artifacts must no longer be copied around manually. Small steps like establishing SSH connections, copying files are no longer needed. And the whole process can be reverted to bring the system to a known working state. The process uncovered also a couple of drawbacks. There is a limited freedom, meaning the user must follow the proposed procedure. There is no verification of dependency relations between the services. We purely rely on the software engineers to properly maintain the dependencies. And the case study, even though being realistic, implies certain type and number of service components as well as certain design choices. Let's summarize our main contributions. We detail and model the domain characterized by network isolation, identify requirements, and update workflow. We leverage satisfiability for dependency resolution, providing alternative strategies with correctness guarantees, and address the trade-off between their execution time and resolution flexibility. We describe an end-to-end architectural design, which we implement as proof of concept, and finally, we evaluate the proposed framework of a realistic case of an air-gapped update elicited from an international organization. We also assess the performance of the dependency resolution procedures for practical problem sizes. This concludes my presentation. Please feel free to ask questions.